The data stream from 3i Atlas has just shifted, and we are witnessing something that defies the standard cometary disintegration models we usually rely on. This is not a gradual fading. This is a sudden, violent shedding event that demands immediate forensic analysis. The latest telemetry, specifically focusing on the recent dust spike, indicates a total mass ejection that is orders of magnitude beyond what a passive sublimation event should produce. We are looking at a localized anomaly in the light curve that suggests 3i Atlas is actively breaking apart, but not in the way we expected. Let's look at the raw numbers derived from the latest optical depth measurements. The signal-to-noise ratio on the trailing coma has spiked. We are detecting a sudden increase in the total scattering cross-section of the object. According to the analysis by Professor Avi Loeb, the calculated dust mass shed by 3i Atlas in this specific event is approximately 10 to the power of 12 grams. To put that in perspective, that is 1 million metric tons of material ejected in a remarkably short window. That matters because a standard outgassing event for a comet of this projected size typically releases material in a steady, continuous stream, governed by the sublimation rate of water or carbon monoxide ice. This is different. This is a pulse. When we model cometary activity, we usually use the H magnitude system to predict brightness based on distance from the sun. A sudden jump in brightness, or in this case, a massive increase in the dust cloud density, without a corresponding decrease in heliocentric distance suggests a structural failure. But look closer at the particle size distribution. This is where the investigation gets truly strange. Standard interstellar dust or typical cometary exhaust is usually composed of micron-sized particles, tiny, smoke-like grains that scatter sunlight effectively in the visible spectrum. However, the photometric data we are analyzing right now contradicts that standard model. The optical depth analysis implies that the particles being shed are not just micron-sized dust. Loeb's latest calculations suggest we are seeing particles that are much larger, potentially in the millimeter or even centimeter range. That matters because larger particles have a completely different mass-to-light ratio. If the cloud were made of fine dust, the total mass would be lower for the same amount of reflected light. But because the scattering efficiency suggests larger grains, the total mass involved in this ejection must be significantly higher to account for the observations. We have to consider the implications of large grain shedding. In our solar system, when a comet like 3i Atlas approaches the Sun, the radiation pressure acts as a sieve. It pushes the tiny micron-sized dust particles away rapidly to form the tail. Larger particles, pebbles, rocks, chunks of the crust, lag behind, following the orbital path more closely. The fact that we are seeing a signature consistent with large particles dominating the shed mass indicates a deeply seated fragmentation event. The object isn't just steaming, it's crumbling. Let's drill down into the calculation of that 10^12 grams figure. This mass estimate is derived by integrating the optical depth over the surface area of the dust cloud. If we assume a standard albedo, let's say 0.04 or 4%, which is typical for dark carbon-rich cometary surfaces, the sheer amount of surface area required to reflect the light we are seeing forces that mass number up. That matters because it gives us a minimum bound on the size of the parent body. You cannot shed 1 million tons of material if you are only 100 meters across. This massive dust spike provides a constraint on the nucleus size that we didn't have before. It suggests a parent body that must have significant volume to survive losing this much structural integrity. Now compare this to the behavior of Oumuamua. With Oumuamua, we saw non-gravitational acceleration but no dust. It was a dark accelerator. With 3i Atlas, we are seeing the opposite extreme, a massive release of particulate matter. That matters because it suggests 3i Atlas is chemically distinct from its interstellar predecessor. We are likely looking at a volatile-rich object that has retained its ices during its long transit through interstellar space, only to violently sublimate them now. But the large particle anomaly suggests something else, a crusty surface. If the surface of 3I Atlas was a simple, fluffy aggregate of ice and dust, we would expect a smooth release of fine particles. The ejection of millimeter-plus sized grains suggests a processed surface, a mantle, formed by cosmic ray bombardment over millions of years. This crust holds together until the internal pressure from sublimating ices beneath it becomes too great. Then it ruptures. That matters because what we are witnessing right now, this spike, is likely a pressure valve, failure on the surface of the object. We are seeing chunks of the ancient interstellar crust being blown off into space. Furthermore, we need to analyze the velocity dispersion of this dust. If these were light particles, the solar wind would accelerate them to high velocities almost instantly. But heavier particles carry momentum. They linger. The persistence of this dense cloud around the nucleus position supports the hypothesis of high-mass particles. Loeb points out that this behavior mimics the disintegration of solar system comets. Yet the scale of mass loss relative to the object's predicted size is aggressive. This leads us to the problem of survival time. If 3I Atlas continues to shed mass at a rate of 10 to 12 grams per event, its lifespan is drastically reduced. We can calculate the depletion timescale. If the object is a few hundred meters in diameter, a series of these events could disintegrate it completely before perihelion.